There's a reason that we do polar equations and functions immediately following parametric equations, because technically polar equations are actually parametric equations. If you take a function, r equals a function of theta. As we had mentioned in the lesson yesterday, you can convert to an x-coordinate by doing r cosine theta and a y-coordinate by doing r sine theta, and therefore you're turning that into parametric equations. So in a similar fashion to the way that we found the derivative with parametrics, dy over dx is actually dy over d theta, because we're not doing things in terms of t this time, divided by dx over d theta. Okay, so one important thing to keep in mind is that the radius is not a constant. So when I take the derivative of this expression and of this expression, derivative of x with respect to theta, derivative of y with respect to theta, I have to treat r like it's its own function and theta like it's its own function. So what am I going to have to use? I'm going to have to use the product rule. Okay, so product rule is first times derivative of the second plus second times derivative of the first. I'm going to start with doing the dy d theta. Okay, so between r and sine theta. R is the first. The derivative of sine is cosine of theta, d theta. D theta, I could put that afterwards. Okay, then plus the second, which is the sine of theta, times the derivative of the first, which is 1 dr d theta. Notice that I'm doing this kind of like implicit differentiation, where I'm following up each variable with d of the variable I took the derivative of divided by d theta. Obviously, the d theta can go away. You don't really have to keep that. Sorry to erase the actual cosine as well. And that would be the top part of my derivative expression, r cosine theta plus sine theta dr d theta. So I'm going to do the derivative of x in the same kind of fashion. First would be r. Derivative of cosine is negative sine of theta, plus the second, which is cosine of theta, times the first derivative of the first, dr over d theta. Okay, so this is where we get our derivative expression for polar equations, if you will. So take a look at example number 1. Find dy dx and the slope of the graph of the polar curve given at the given value of theta. So let's start with the fact that, again, dy over dx is going to come really from dy over d theta over dx over d theta, which came from the formula that we have above. You know what, actually, you don't have to write this part down. Just go right to using the formula that we have above. R cosine theta plus sine of theta dr d theta, and negative r sine theta plus cosine of theta dr d theta. Okay? I know that probably feels like an overwhelming formula to memorize, but again, keep in mind where it came from. It was parametric equation derivative using x equals r cosine theta and y equals r sine theta. Okay, so just keep that part in the back of your head. For today's lesson, just keep rewriting this down as you go through each of your problems. Okay, so our r function is 2 plus 2 sine theta. Okay, so dr d theta, the derivative of this r expression. Well, derivative of 2 comes out to be 0. Derivative of 2 sine theta becomes 2 cosine theta. Okay, so if I complete this a little bit more, my r was 2 plus 2 sine theta. My cosine theta is just going to stay cosine theta. Sine of theta is just going to stay sine theta. And then dr d theta becomes 2 cosine theta. In the denominator, I have negative times r. R is still that whole expression. 2 plus 2 sine theta multiplied by sine of theta plus cosine of theta times 2 cosine theta again. That's dr d theta. Okay? In terms of finding the derivative, there's nowhere that says you have to simplify it. I would probably say I don't think you should simplify it unless it truly makes your life easier. I would leave it just as is and then plug in the given value of theta that they ask you for and then evaluate it at that point. Okay, so if you want to see like the entire derivative fully worked out for when you evaluate it at pi over 2, just take a look at the solution that I posted in our Google Drive. This one actually evaluates entirely to come out to be 0. That really a lot has to do with the fact that cosine of pi over 2, if you think of your basic cosine curve, pi over 2 is this first 0, makes all of these terms turn into 0. So really in this case, I only really have to evaluate what's in the bottom left to make sure that I'm not getting 0 over 0. Keep in mind, if you get 0 over 0, that doesn't mean does not exist. That would mean that you'd have to do more algebra, and obviously, again, in these kinds of situations, this would be very, very, very complicated to have to do more. So I don't think you have to worry about that. I would say, in terms of remembering trig functions, you really want to make sure you know your basic sine and cosine curve. I think a lot of these values are going to come from that or your special right triangles. Take a look at example 2 now. Find the points r theta of horizontal and vertical tangency for the graph of 2 minus 2 cosine of theta. Okay, so my dr d theta, the derivative of r with respect to theta, 2 is obviously going to come out to be 0. Negative cosine theta would normally come out to be positive sine theta. So that's where I get 2 sine theta as my dr d theta. And then what we're going to have to do is we're going to do that same formula we just did in the last problem. dy dx comes out to be r cosine theta plus sine of theta dr d theta all over negative r sine theta plus cosine theta dr d theta. Okay, so we fill in the values from above. R is 2 minus 2 cosine theta, obviously times cosine theta, and then I have sine of theta times 2 sine of theta. Okay, and then in the bottom, negative 2 minus 2 cosine theta, sine of theta. Sorry, now it takes a little while just to even just write these out. But I still just want you to see exactly how I work through a problem like this. Okay, so what do we want to do if we want to find out where I have horizontal or vertical tangents? Basically what you're going to do is you're going to think about how do you make the numerator equal to 0. Okay, that's what happens when you want to have horizontal tangents. And then denominators equal to 0. That's how you're going to find vertical tangents. You should know any place where you have 0 in the top and the bottom cannot count as a point of tangency. That would actually be a place where the tangent does not exist. Okay, so what I'm going to do in this video is I'm going to work through how you find where the denominator is equal to 0. If you would like to see where the numerator is equal to 0, go to our solutions in Google Classroom, on Google Drive, and you can see the entire problem worked out. I think where some of you are going to struggle is that this is now becoming something like solving trig equations. So there's some trig identity stuff in here that you're going to want to think about. An important trig identity is that sine squared theta plus cosine squared theta equals 1. You should also keep in mind things like 2 sine theta, cosine theta is the sine of the double angle. There's a couple different versions of the cosine of the double angle. You know, again, each of these is going to have different situations you want to think about. So, like I said, if you want to see how you find your horizontal tangents, go ahead and take a look at our solutions. For this video, I'm going to work on doing our vertical tangents. So let me get rid of all this stuff for a second. And I'm just going to set the denominator equal to 0. One more time, let me move this guy over. So, I'm going to set this equal to 0. This is how I'm finding, in this case, my vertical tangents. Okay, so if I can kind of clean this up a little bit, I have negative 2 minus 2 cosine theta times sine of theta plus 2 sine theta cosine theta. If I distribute this sign inside this parentheses along with that negative, this will become negative 2 sine theta. This will become a positive 2 cosine theta sine theta. And I have here another positive 2 sine theta cosine theta. So if I combine those together, that becomes 4 cosine theta sine theta. Okay, I don't actually end up needing any of the trig identities for this problem. I don't know how long it's been since you looked at trig equations, but this is one that's actually factorable in the way that it's already written, even though it's not in terms of one trig function. I can factor out of this sine of theta. In fact, maybe I'll even factor out a 2 sine of theta. Once I do that, I'll be left with negative 1 plus 2 cosine theta. And then I'll just go through and finish solving each of these individual equations. As with any kind of like quadratic style equation, you set each of your factors equal to 0. So in the bottom left one, I'm looking for where does sine of theta equal 0. We'll look at your basic sine curve. Sine equals 0 when you're touching the x-axis. So that would be at 0, pi, and 2 pi. Now, I have to be careful because when I did the solutions for the horizontal tangents, 0 and 2 pi actually worked for both horizontal and for vertical, for numerator equals 0 and denominator equals 0. So actually 0 and 2 pi then cannot count. So the only one where I actually have a vertical tangent is at the point pi comma something. Okay, again, I can't do 0 and 2 pi. Then I'll take a look at when I have -1 plus 2 cosine theta equals 0. This becomes 2 cosine theta equals +1, or cosine of theta equals 1/2. If you think of this in terms of degrees for a second, ASTC would tell you that you have positive cosine in the first and the fourth quadrant with a reference angle of 60. 60 is really pi over 3, and 60 is really 300, which is going to be 5 pi over 3. And so therefore I have these two values that don't match up with any of the values from the previous portion of solving. So I'm going to end up having points at pi over 3, and at 5 pi over 3. And then to finish making the full points, notice that in the directions it says points, not just the r values. You have to take each of these values of like pi over 3, 5 pi over 3, and you're going to have to plug all of those back into the original r equals 2 plus 2 cosine of theta. Okay, so let me just do like one or two of these just to evaluate. So if I did 2 minus 2 times the cosine of theta, if you think again about your basic sine and cosine curve, cosine is going to be equal to -1 when I'm at pi. So I have 2 minus 2 times -1, which becomes 2 plus 2, and that's where I get the point pi comma 4. If you want to do the one at pi over 3, this one involves a little bit of special right triangles. So 2 minus 2 cosine of pi over 3. Well, cosine of pi over 3 is really cosine of 60. As we had just seen from our previous stuff, cosine of 60 was 1/2. So 2 minus 2 times 1/2 comes out to be 2 minus 1, which comes out to be 1. And then finally the last one, if you go through and evaluate, when you plug in 5 pi over 3 again, that's talking about a cosine value that's in the fourth quadrant, so that still comes out to be a positive 1/2. Okay, so this is 1/2 of the solutions here. And again, if you want to see the rest of the solution, just so you can see another trig equation worked out with some identity stuff, you can go ahead and look at the solutions that I posted for this problem in Google Classroom. Let me just talk about really quickly if you had to actually create, a tangent line, like you can see in example number 3 here. So it says determine the equation of the tangent line at pi over 6. So in a similar fashion to what I did in the previous problems, I'm going to start with my dy dx being that formula r cosine of theta plus sine of theta dr d theta all over negative r sine of theta plus cosine of theta dr d theta. Okay, like I said, I know the formula might seem overwhelming at first, but I think it's one of those ones that if you write it down a couple times, I think you'll remember it. You realistically are not, going to have to worry about remembering it right now, especially because we don't really have an AP exam that incorporates the polar and parametric. But, just in case, it just still comes from doing parametric to the x and y coordinate based on converting from polar into Cartesian. Okay, so if I plug into this problem, my dr d theta is going to be equal to 8 cosine theta. So let me write all this stuff in. So I have 3 plus 8 times the sine. I'm going to go right ahead to plugging in the actual theta itself instead of wasting the time to write all this in. So 3 plus 8 times the sine of pi over 6, that's my r. Then I'm multiplying that by the cosine of pi over 6. I'm adding the sine of pi over 6. And I'm multiplying this by 8 cosine of pi over 6. Okay, in the denominator, I have negative 3 plus 8 sine of pi over 6 times the sine of pi over 6 plus cosine of pi over 6, and then 8 cosine of pi over 6. Unfortunately, we're not as lucky as we were in one of the previous examples when we were trying to evaluate a derivative value at a specific point. None of these are going to work out to be 0. But what I will point out is that pi over 6 is basically 30 degrees. So everything that I do in terms of sine and cosine is going to come from the 30, 60, 90. So you're going to have a lot of things that are going to be 1/2 or a radical 3 over 2 or something like that. It's all acute angles, so they're all going to be positive. So if you take the time to go through and plug all this in, eventually you'll see that this works out to be 11 radical 3 over 5. Okay, so how does that fit into writing the equation of the tangent line? Well, if you think about our formula for the equation of the tangent line, L of x equals f of a plus f prime of a times x minus a. The a and the f of a and the f prime of a is the thing that's a little tricky this time. dy dx is f prime of a. So this is basically my f prime of a that we just calculated. Okay? My a and my f of a come from the x and the y coordinates of the point on a line, on a curve. In this case, I can't use r and theta. I want actually x and y. So if you think about the fact that x is equal to r cosine of theta, so that means I'm going to do 3 plus 8 sine of theta, pi over 6, times cosine of pi over 6. You'll see that that works out to be the value 7 radical 3 over 2. If I then do y equals r sine theta, so 3 plus 8 sine of pi over 6 times times sine of pi over 6. That comes out to be 7 over 2. This is technically my a, and then this is technically my f of a, because that's the x and the y coordinate of your point of tangency. So if you put all this back together, you'll have L of x equals f of a, which as you can see right here at the bottom, the 7 over 2. Okay, plus f prime of a plus 11 radical 3 over 5 times x minus a, x minus 7 radical 3 over 2, and you would leave your answer just like that. There's no simplification or anything needed. The most important thing I wanted to show you in this problem, not only how to evaluate something like pi over 6 equals, 30 degrees and get some of those exact values, but also how do you actually do the tangent line for this. So again, remember, you're still doing normal L of x. The tricky part now is, though, you can't be using r and theta for a and f of a. You have to actually find out what is the x point of where you're making your tangent, what is the y point of where you're making your tangent, and what is the derivative of y with respect